Right, so now we're going to cover the individual electrolytes and what happens if you have too many or too few of them. We're going to start with potassium because potassium really is probably the most interesting of them. It has the greatest effects, clinically speaking. When potassium starts going wild, it has a profound impact on the heart in particular. And so that's why it is extremely important to know how it works. So, as we discussed before, potassium is basically like the cats, and the cats are all supposed to be inside the cell, hanging out, and this is incredibly important specifically for the heart because the heart keeps count for how often it wants to beat in the weirdest way possible. It basically counts the cats or the potassium as it leaks out of the cell. And when enough of it leaks out, it says, okay, I guess that's good. And so it goes through a contraction cycle. So, in particular, the SA node in the heart is the biggest pacemaker. And the reason that it's an important pacemaker is because it has a bunch of holes in it, basically. It's super permeable specifically to potassium. And so it's also super vulnerable to changes in the amount of potassium in the blood. Normally, you have a whole bunch of sodium outside, and you just have a little bit of potassium. There's like four potassium out here. And so the cats are like, okay, well, we have food and water and everything, so we kind of like being inside the cell, but there's also way too many cats inside. There's too many of us cats, and so we're really thinking about going outside, checking it out, kind of easing the crowding inside the cell a little bit. And so they have these little windows, and under normal circumstances, they crawl out of the little windows at roughly a rate so that your heart beats like once a second or so. And so this is all kind of regulated by the number of cats outside. Because like I said, the cats inside don't really like cats, and so if there's more or less cats outside, it changes the willingness of the cats inside to exit. So we're going to start with hyperkalemia because um, hyperkalemia has its own really specific effects. So let's say that there's more cats outside. The cats on the inside are going to look out the windows and say, that's a lot of feral cats outside. Um, I don't really like that. At first, it's not really that big of a deal. It's just a few more cats, and so potassium is it still leaves the cell at roughly the same speed. And in fact, it will actually speed the heart up a little bit at first. You'll get a little bit of tachycardic with just a few extra cats outside because the cats will leak out roughly the same. And when the doors get thrown open and it's time for the family to collect their cats and throw them back inside the house, there's extra cats outside. And so the cell membrane actually can repolarize a little bit quicker because the family doesn't really care which cat it is. It just wants to have 140 cats inside. So it just grabs whatever it sees, and since there's a few extra cats, it can chuck the cats out a little bit quicker. And so in this case, the cell can repolarize the membrane a little bit faster, and you get a little bit of tachycardia, but this is only at the very beginning. This is only with minor hyperkalemia. As that continues to go up, though, the the effects of the extra cats outside kind of overwhelms this effect. Okay, so that's just to begin with. The way that this looks on an ECG is that, like I said, the depolarization or the repolarization happens a little bit more suddenly and a little bit more easily than usual. And so, if you remember on your ECG, this is the atrial depolarization, this is the ventricular depolarization. The T wave is when the ventricles are repolarizing, and this is the since the repolarization of the atrium basically is underneath the depolarization of the ventricles, you can't really see anything that happens there. But here, you get little bit of a peak because it happens quicker than what you're used to seeing. Normally, it's kind of a systematic thing. The family goes out, grabs some cats, works them back in. But now there's so many cats out there that all they have to do is open the door, and there's just cats waiting. So you see this little peak T wave because it's easier to get cats back inside than usual. As the number of cats outside goes up, though, you start getting a little bit of effect of the unwillingness of cats inside to go outside anymore. Because now they're looking out the window and they see like 20 tomcats out there, and they say, you know, I've got food and water in here, and if I go out there, I'm going to be in trouble with all of those feral cats out there that really would just rather have what I have. They don't have owners to scratch them and stuff like that, so I don't think I'm going to go out there. And so the rate at which cats are willing to leave gets cut a little bit. It's a little bit slower. And so you start seeing a slowed depolarization of the ventricles, and it also tends to slow the rate at which the neurons that carry the cardiac wave signal through the heart, those don't want to depolarize either because their cats don't want to go outside. And so everything just kind of slows down. And so you start getting bradycardic, because everything just takes a little bit longer. Even though you can still repolarize a little bit easier, the most important part of the wave, as you can see, all of this is mostly depolarization. So a big part of it, it has a more profound effect for this to take longer than for this to take less time. Okay? So when this starts happening, you start seeing a lot of widening. So like the PR interval widens, the QRS complex can also widen because all of this just takes a little bit longer. Not only does it take longer for the contractions to happen, but it also takes longer for the signal to contract to travel down the heart and down to the ventricles. And so these things get a little bit wider, and also this has a tendency to kind of like flatten out because the depolarization happens slower. And as this gets higher and higher, eventually this can disappear entirely. The P wave will just flatten out because the leakiness of the cells, especially in the atrium, cause it to reach a point pretty quickly where the cats just aren't willing to go outside anymore. They just won't do it. And since the whole heart rate is being controlled by their willingness to go outside on their own voluntarily, at some point they just won't. And so the atrium will basically just stop. It'll become paralyzed, and it won't be able to repolar or depolarize at all anymore, and this stops entirely. And so eventually you see the T waves, since it gets easier and easier to repolarize, the T waves will get bigger, the P wave will disappear, and this will get longer. And so that's when you start seeing what they call the sine wave. Because instead of having all of these really obvious individual elements, it kind of just turns into this. And you can't really differentiate anything anymore. This usually means that the atriums have basically stopped entirely. They're paralyzed. You're just completely dependent on passive filling for the ventricles. So the cardiac output is going to absolutely plummet. And the only thing that's really beating anymore are the ventricles. And this is like right before the ventricles will stop too. Eventually, even the ventricles won't be able to depolarize anymore. The AV node won't be able to compensate, and you'll basically just have complete heart stoppage or blockage. Obviously, bradycardia, reduced pumping of the heart, that causes hypotension because you're not moving as much blood anymore. And this also has effects on pretty much all of the muscles of the body. Really, the most important one, other than the heart, is the diaphragm, the lungs. When you can't get the muscles to activate, you will see respiratory depression. Um, and so the breathing will slow down. You'll get general muscle weakness. You'll get depressed deep tendon reflexes. The reason for this is that your reflexes are also based on the ability for the neuron to depolarize or repolarize. And since the cats don't really want outside anymore, when your reflexes are usually based on changing, like physical changes in the membrane of the neuron that senses the reflex. And so when the membrane changes, it makes it a little bit more permeable. But if the cats don't want to leave anyway, it really doesn't matter how permeable the membrane is. You can add 10 more windows there, which normally would set off a reflex, but in the case of too many cats outside, they're just not going to go anywhere. And so your reflexes also go down. You're also going to see some CNS effects because obviously the whole nervous system is based on polarizing and depolarizing cell membranes, and so you're going to have some effects there. But really, these are the most dangerous. If the heart stops, it really doesn't matter what else is going on. As far as common causes of this go, one of the most common, most likely to be tested on, most clinically significant effects of this is tissue destruction. Because as I put here, potassium is the most abundant electrolyte on the inside of the cell. So normally potassium can't really cause any problems because everybody's keeping their cats inside. But let's say that a patient gets significant burns, the whole neighborhood burns down. When all of those houses are going down, you know that those cats are going to figure out how to get out of that house. Okay, all the cats are going to escape. They're going to make it out of the neighborhood, but now there's no houses for them to get picked up into, and so all they can do is wander off. And now they're all feral cats too. And so these are all basically just homeless cats. They used to have a home, and their home got destroyed, and so now they're out looking for a new place to call home, and it causes issues through the whole neighborhood, the whole city. Now we have way too many cats. Another common cause of this is metabolic acidosis, and the reason for that is when things start getting real acidic in your blood, not necessarily in the heart, but like in any cell, you got a bunch of protons. This is what causes your pH to go down, is having too many free protons out hanging around. And so I kind of liken these protons to like toddlers. If you look out your window, you're like a responsible family. You look out your window and you see a bunch of extra toddlers wandering around, and you don't know who they belong to, and you don't really know what to do about it. What you're probably going to do, in order to keep those toddlers from getting hurt or causing havoc in the neighborhood or whatever, you're going to pull all of these toddlers into your house. And you're going to say, okay, well, we'll figure out what the hell to do with them later, but for now, let's get those toddlers indoors. But it's really not great to have a bunch of toddlers in your house and also have 140 cats. So these responsible homeowners decide to start chucking cats outside because these toddlers are going to cause more obvious problems. And so they decide that it's better to exchange toddlers for cats. And so all the cats get kicked out, and now the neighborhood is toddler free, but it's filled with a bunch of feral cats. And so this causes problems as well because it's basically a compensatory mechanism for metabolic acidosis. This is commonly treated with insulin as a really common treatment for this because insulin is kind of like a homeowners association representative that goes around the neighborhood causing all kinds of problems. Insulin comes through and it sees all of these cats out in the yard, and it says, well, I know how, I'm really good at making this family pick things up. And so it goes to the door and it knocks on the door and it says, hey, you got to get all this junk off of your lawn. And so normally this is only used to tell families to go pick up their like glucose, like grocery delivery, like Kroger delivered, and they left it out on the porch. And then the homeowner's rep insulin comes by and says, hey, pick your crap up. And so they stuff it inside. But it also works for cats. If insulin comes by, insulin also is really good at working on these active transport channels for potassium. And so it comes and knocks on the door and says, pick your stuff up. And so the cells not only start picking up glucose, but they start picking up potassium too. They'll start shoving all this potassium back into the cell. So insulin works really good for that. It can also cause hypoglycemia because these guys, they see the HOA rep, they don't really want problems, so they just start picking up everything that they see. They'll pick up their groceries, they'll pick up their neighbor's groceries, they'll pick up the whole city's worth of groceries if they can figure out how to do it, and they'll keep picking up glucose until the person is hypoglycemic. So oftentimes, if you're going to use insulin to treat hyperkalemia, you will also administer glucose to them so they don't end up hypoglycemic. There's a few other treatments for it. There's like Kalemia, which basically runs through the GI system, and it basically prevents the absorption of potassium, and it creates a concentration gradient out. It absorbs all of the potassium that's in the lumen of the GI tract, and so the cells that line the GI tract will start chucking potassium out there to kind of try to equalize things, and so your body will eliminate potassium through the GI tract. Normally, though, it's just excreted in urine, and it's not really that big of a problem unless things get out of control. So once again, you have your peak T waves because repolarization is super duper easy, and then everything else gets a little bit longer, and in some cases gets a little bit flatter because it takes longer to depolarize and to convince all the cats to leave. I think that pretty much covers hyperkalemia. Now let's go to hypokalemia, which is basically the opposite problem. Now we have only a couple of cats outside. So these cats, they're super happy to leave because they look outside and they say, man, I could go on an adventure and there's not really any feral cats out there to harass me and cause me problems. So these guys they're fine with leaving the house. They'll bounce, no problem. And now, normally, they wouldn't really wander too far from the house because, like, yeah, they got food and water and family that loves them in there. They don't really want to go too far. But now there's really not any feral cats outside to like kind of keep them around. And so when they get out, they don't just kind of stop. Like they'll just keep going. And so when the family realizes, hey, we're missing a bunch of cats, let's go look for them, and decides to open the gates and take a gander for some cats, there's really not as many of them outside as would make it easy for them to repolarize the membranes. And so they have the opposite here. Instead of this wave getting real tall, this wave kind of flattens out. And in fact, you'll even get another wave that you don't normally see too much of, but the U wave. It's an extra wave that kind of pops up when it's taken a little bit extra effort to repolarize the ventricles. And the nerves that carry the conduction of the contraction wave, those have to repolarize, and so you get this extra little wave here because, and sometimes it can be even more prominent than the T wave. The T wave can mostly disappear, and the U wave is mostly what you see, and this is because it's really struggling to repolarize. And then you also see another interesting thing in situations where you have hypokalemia. This is hypokalemia. Because the repolarization of the atriums are usually hidden under the QRS complex, you don't really see that part. But hypokalemia kind of changes that a little bit because now the cats are super willing to go outside. They'll go outside quick, and so you get more narrow peak when the ventricles depolarize because they'll depolarize really quick. The cats are more than happy to go outside, but the repolarization takes a little bit longer for the atrium, and so the repolarization of the atriums isn't complete when all of the cats are already gone, and so you get this real deep notch here right around the S area, and then it'll kind of come back up, and so this is called ST depression. Not to be confused with the kind of depression that most of us have. ST depression happens right here, and it's just this extra little notch that you don't normally see, caused by the atrium just taking a really long time to repolarize itself. Let's see, you get the other effects. It also has similar effects on the muscles because muscles are all based on a bunch of contractions to make the effects happen. It's like a bunch of contractions that add upon each other, and so when things take longer to repolarize, your muscles also end up weak in this scenario as well. You can also get muscle cramping because the nerves that conduct the signals to activate your muscles have a really hard time repolarizing and basically deactivating, and so the signal kind of persists, and they can get activated really easily. Um, the membranes become a lot easier to depolarize because the resting membrane potential is just a little bit closer to activation at all times. Once again, you end up with respiratory issues, possibly a little bit more notable in hypokalemia. And the reason for this is that like Ms. Bridges said, the diaphragm is a muscle. It's a very important muscle. And so when it gets weak, it can't pull the lungs open as far, okay? It just kind of maxes out real shallow into the breathing cycle. And so in order for your body to like compensate for the fact that you can't pull your lungs open far enough, it increases your respiratory rate and makes you breathe faster. So you see shallow breaths, but you can also see tachypnea with this because your body's trying to breathe a little bit faster to compensate. In the case of hypokalemia, you pretty much always see bradycardia because everything just takes longer. The repolarization just takes longer, and so the cycles between contractions takes longer, and the heart rate drops. Most often, this is caused by diuretics. Diuretics cause the body to kick mostly sodium out, and I don't think it's really worth getting into the interplay between sodium and potassium in the kidneys. But when you're losing sodium, you pretty much by default tend to also lose potassium because your body makes trades. You can also see this this is also really associated. Hypokalemia is also really associated with metabolic alkalosis. And the reason for that is one of the things that your kidneys try to do is it looks at the filtrate going by and it sees potassium out there and it says, hey, I kind of need the potassium. I kind of like cats. So I should pull one of those cats inside and pick it back up. But it always wants to make an even trade. So similarly to how hyperkalemia happened by pulling toddlers in at the kidneys in order to get potassium back inside, it has a tendency to want to throw toddlers out. And so if you're if you're in metabolic alkalosis, you don't have enough toddlers laying around, and so your kidneys are like, well, I guess I should just let the cat go because I can't really be throwing all these toddlers out when I only have a few of them laying around. So you see an association there. Hypomagnesemia is also heavily associated with hypokalemia. These are associated because, like I said before in the previous section, magnesium is really good at blocking things, and so one of the ways that potassium gets out of the body, obviously, is being excreted in your urine, and your kidneys have these doors that it likes to let potassium go through. Normally, this is pretty much well regulated because magnesium is hanging around in those doorways, and so potassium can't really get through and kind of blocks all that stuff up. But if you are really low on magnesium, you have a tendency to also then become low on potassium because those doorways are no longer blocked, and so potassium just kind of leaks out into the filtrate, and your body loses potassium that it otherwise wouldn't if the magnesium mechanism was properly blocking that from happening.